Let's move on to part B. We are going to talk about how a new element is going to be inserted into a heap. All right. In the NQ operation, also known as the insert operation. Now, adding a new element is not an issue, but we need to make sure that we need to preserve the two properties, the CBT property as well as the heap order property. So let's look at this example. This is A. All right, it is a heap. It has met the two requirements. If some new node needs to be added, in order to make sure that it is still a complete binary tree, the new element needs to be added here. No choice. Okay, let's say we are trying to add this node. The key is 2. This will be the outcome. Now, however, at this point in time, we do not meet the second requirement. The heap order property is not met. So something else needs to be done. It's not as simple as, now if this were an array or a list, so we have, 4C here, 5 here, 6 here, and so on. The last element is 13. I'm just showing the key, but right, the value should be shown as well. So adding a new element or a new node at this particular position in blue is as simple as inserting the new node here, the last position, correct? Basically, this will be automatically the child, or in this case, the left child of node number 20, this one. Now, the problem is this second requirement is not met, so we have to do something extra. We need to do this thing called up-heap bubbling. Okay, what do I mean? So now I'm at B already, huh? Okay, I will compare this with its parent. Remember, for a minimum heap, the parent must be smaller than both children. So in this case, this is not true, right? So I need to do a swap. I swap this node with this node, the parent node, okay, as shown in figure C. And after the swap, I'm left with 2 here and 20 here. Are we done? No, because this thing may still not be in the correct position. I need to ensure that the node number 2 or node T is smaller than its parent, okay, which is not the case. So I need to perform a swap with its parent, and I'll be looking at state F now. Again, is this done? No, not yet. I need to check that this is in the correct position. Is it smaller than its parent? No. Perform another swap, and this is the final state. Element, the node with the key of 2 is the parent. So there's no, you carry on, we call this bubbling up. This is called upheap. We carry on upheaping the node until it is at the correct position. It means until it is smaller, is bigger than its parent, you stop there. Or until, for example, in this case, it reaches the root node. So these are the two stop conditions when you perform an upheap. Okay. So this is the Python code for inserting a new element. Okay, remember, there are 2 steps here. The first step, assumption here is that heap is a list. The first step is to just insert the new element at the last position of the index. So this is the index. This is the array or the list. This is the root, right? All the way here. So it's as simple as appending the new node here. Okay, that is the first step. The second step, then you do the up-heap bubbling. Okay. So in this example, I just pass in a key here. This actually is a node. It is not a key only. The node will consist of a key and a value inside. So to make things simple, I'm just passing in a key lah. Actually, what you need to pass into insert is actually a whole tree node, which consists of key and a corresponding value. So after adding the new key or the new node to the last position of the list, we call an upheap method, which is here, or the upheap function. And what do we pass to upheap? The position of the newly inserted element, which in this case is just n, or length key minus one. All right, the position of the newly added key or element. So what does upheap do? Okay, so upheap repeats a big while loop. It stops only when it reaches the break statement, and that will happen when that current element is at the correct position. That means its parent is actually smaller than itself. Or it reaches the situation when j is equivalent to 0. That means j is at the root position or the first position of the list. So these are two stop conditions I mentioned just now. So what do? P equals to parent j. I'm trying to determine the parent of j. So this is the array or list, right? So this is the newly inserted element. All right, j, this value j. I'm trying to look for its parent. So its parent is somewhere in front. So this is the parent of j. And then what do? I compare the value of j with its parent. So if the parent is smaller than the j's value, end of key, end of story, I break because it's at the correct position. On the other hand, if that's not the case, I need to do a swap. So this statement does the swap. And then j is now a parent. So I do a swap. This swap with, so in this example, let me go back to this case. In this example, I'm swapping this with this. All right. Here it is. And then now I'm keeping track of j. J is now at position P. And I repeat the while loop to check who is the parent of the element of that node, and is there a swap required, and so on. So that's how upheap is written. Okay. I'll stop here.